On this and the following slide, we illustrate the calculation of delta Rg at a given stage of a reaction to determine whether this reaction proceeds spontaneously or not at that time. For this purpose, we consider the reaction of hydrogen gas with iodine solid to form 2 moles of hydrogen iodide. The standard formation Gibbs energy for hydrogen iodide gas is 1.7 kilojoules per mole. For this problem, we want to calculate delta Rg when the total pressure is 2.000 bar and the mole fraction of hydrogen iodide in the gas phase is 0.2000. First, we write delta Rg equals delta Rg standard plus RT times the natural log of Q, where Q is the ratio of the square of the activity for Hi to the product of activity for H2 gas and activity for I2 solid. The square for the activity of Hi reflects the stoichiometric coefficients of 2 for Hi in the reaction equation. The activity of Hi is the ratio of the partial pressure of Hi to the standard pressure. The partial pressure of Hi is given, according to Dalton's law, by the product of the mole fraction of Hi in the gas phase and the total pressure. The activity of H2 is the ratio of the partial pressure of H2 to the standard pressure. The partial pressure of H2 is given, according to Dalton's law again, by the product of the mole fraction of H2 and the total pressure Pt. The mole fraction of H2 is equal to 1 minus the mole fraction of Hi in the gas phase, since H2 and Hi are the only constituents of this gas phase. The activity of iodine is equal to 1, since iodine remains as a pure solid during the reaction. Combining the activities of iodine, hydrogen, and hydrogen iodide in the expression for the reaction quotient, we get Q equals xhi squared divided by 1 minus xhi times the ratio of P total divided by P standard. The standard reaction Gibbs energy change, delta Rg standard, is equal to 2 times the standard formation Gibbs energy change for Hi gas, that is 3400 joules per mole. Hence, delta Rg equals 3400 joules per mole plus 8.3145 joules per mole per Kelvin times 298.15 Kelvin times the natural log of 2 times 0.2 squared divided by 1 minus 0.2, which leads to delta Rg equals minus 2308 joules per mole. Since delta Rg is negative, the reaction to form Hi from H2 and I2 is proceeding spontaneously at the time the mole fraction of Hi in the gas phase is 0.2. We now carry out the same calculation at a later stage of the reaction when the mole fraction of Hi in the gas phase has reached a value of 0.3. Calculations follow exactly the same path as on the preceding slide, except that now delta Rg is given by 3400 joules per mole plus 8.3145 joules per mole per Kelvin times 298.15 Kelvin times the natural log of 2 times the square of 0.3 divided by 1 minus 0.3 equal to plus 33 joules per mole. So we conclude that for a mole fraction of Hi equal to 0.3, the reaction would not be spontaneous in the direction that forms Hi from H2 and I2. As the reaction proceeds from pure reactants, it would reach an equilibrium for a mole fraction of Hi above 0.2 and slightly below 0.3. Above that composition, the reverse reaction, that is, the splitting of hydrogen iodide into hydrogen gas and iodide solid, would be spontaneous.